Hello, everybody. Welcome to Markov Processes. My name is Jem. I'm going to be your guide for the journey ahead in the spring 2023 semester. That's obviously remote. I am so glad you signed up for this course. I love to get to teach it because Markov chains or Markov processes are, it's my area of research. So at the end of the semester, once we have a lot of knowledge about Markov chains built up, I want to show you some pretty cutting edge things going on in the Markov chain literature. So I think the first thing we should do is get the details out of the way. Let's take a look at the course Canvas page. If you go to the course Canvas page, the first thing you're going to see near the top are announcements. And this is my main method of communicating with you. So if you don't have notifications for announcements turned on, I would do it because maybe you're going to spend a long time struggling with some problem and it turned out it was a typo and I had posted it up here. So it's not that I ever have typos, but you know what I mean. It's a good place to see important, timely information. So scrolling down a little bit, I just wanted to say something about this animated GIF, I guess. And this is a queue. So queuing theory is the science of standing in line. And queuing theory is huge. It's a huge application of Markov processes and one that we're going to spend a lot of time on. So that's why that's here. We're going to learn the best ways to stand in line and what other kinds of things we can apply that to, like information packets on the internet and other things that don't look like people standing in line at all, but really act the same way. So the syllabus is here, which is probably one of the most important pieces of information, but I'm going to come back to that. Down here, there's some buttons, and here is the live lecture Zoom. So this is a link to this class, which is going to meet Monday and Wednesday from 4:40 to 5:55 p.m. And I'm recording the lectures and will post them. And I don't have a mandatory attendance policy, but you are strongly encouraged. You have to have a lot of discipline to keep up when you're not actually going to class. I've seen too many people now in the last 3 years of remote stuff just drift away if they don't come to class. So I would strongly recommend it. I have 3 office hours listed here, and here's a secret. Every one of these 4 links is the same. So if you just want to bookmark a link and stick with it, you'll be in good shape. We also have a TA and possibly another assistant who will be holding office hours, and I will get those hours to you as soon as I know them. Okay, so if you've taken a course with me, you might have seen one of my drafts of books or collections of notes. I do have one for this course, and it's on this button right here, Evolving Course Notes. If you click on this, something really slow will happen. You'll see my Markov process notes. Now, these are not nearly as polished as some of my others. I only have 231 pages, and all the material is there for the most part. I actually am adding a new topic at the end of this course called renewal processes. But this is being updated and updated often, constantly changing and trying to get away from you. So I will try to get all my updates done in the very first couple of weeks of classes. So if you happen to be a person that, a couple of people still print out notes, and I wouldn't do that now because they're going to change, but not drastically. So there you go. That is the notes. I will have some recommendations when we look at the syllabus for some other textbooks you might want to look at. You don't have to at all, but some people are not comfortable not having an official textbook. So I put some there, but they're not official. So this button for modules is, I think, the most important button. This tells you what we're doing from day to day. So if you click on it, there's going to be a list of modules associated with each class. And these are going to come up just a little bit before the class, probably in the same day. Each module will have a date on it. So here is January 18th, and that corresponds to when the live class was, or in this case should have been because we had a snow day. And if you go in here by clicking on objectives and readings, you'll get a list of what we're going to talk about that day, and then sections of the notes that I'd recommend reading. And then in here, I will be posting the video. So I'm going to post this probably very late in the evening on the same day, or at worst, early the next morning. And the reason for the delay is because I really want you guys to be involved and participate and speak up. You could just say things. You don't have to raise the little hand emojis, or put a question in the chat, and you could put it publicly or privately. But I want you to stay involved, and I don't want you to be shy about, am I going to post this on YouTube or something? So the reason for the delay in posting the lecture is I go through and scrub you out like you never existed. I'm going to take away your face and your voice and any reference to your name. And so that's the delay, but I'll try to keep it as small as possible. The final part on this modules page is where the assignments will be. There's going to be a weekly assignment coming out on Wednesday and due the following Wednesday. And you're going to hand in those assignments on Gradescope. So there's a Gradescope link up here. I am not going to click on it because I don't know what kind of view that's going to be. I don't think it's going to be your view, so I don't think it's going to be very helpful. I think it's pretty self-explanatory, and I know a lot of you have used it already, but we'll talk about it at the time of your first submission in case anyone doesn't know what to do with Gradescope. So let me go back to the main page. I guess it is time to go to the syllabus. Okay, my office is ECOT 649, but I will not be in there. I am away from campus this semester. And if you go there, it won't even look like I'm there because I just moved my office and there's an old name plaque on the door that's not mine. I haven't put mine up yet. We have a TA, Evan, and someone else potentially. And again, when I get the office hours and whether they're going to be in person or Zoom, I will let you know. So down here, I've got the textbook, which is the notes I'm providing. And if you want more references, you go to the very bottom of this page. I have 2 PDFs of books here that I really like. This bottom one, An Introduction to Stochastic Modeling by Taylor and Carlin, I think is a great book. It's just a tiny bit low for the level of this course, but really easy to read and has most of the same topics, maybe all of the same topics, except for the simulation. And so there's a PDF linked here. I won't load that up because I don't want any delays like that. This other book on top, Essentials of Stochastic Processes by Rick Durrett, is a very good book, and it is the right level, but this is going to be on video, so I need to be careful, but I personally don't think it's the greatest first look at Markov processes. I think it's a little bit harder to read than it needs to be. It's an awesome book, but it's good to have on your shelf after you know Markov chains, or maybe you want to learn from it. But there's also a PDF link there. So let me go back up to the top here. After the textbook, I have a topic list. You can also look at the table of contents in the book, but these are some of the things we're going to do. And homework. Okay, so I said Wednesday to Wednesday. And because the class is quite large, I can't accept late homework. It just turns into a nightmare because it gets out of the queue. We were talking a little bit about queuing already. And once it gets out of the grading process, then it completely stalls somewhere. And then at the end of the semester, after I've graded the finals, I spend another week and a half catching up on homeworks, and it just doesn't work. And so I'm going to stick to a no late homework policy. They are due on Gradescope by 11:59 p.m. on the Wednesday that it's due. And in case you can't do it 1 week or 2 weeks, you're going to get 2 lowest scores dropped. And if you have a real documented medical emergency, then we can talk about that privately. There is a simulation component to this course. This is not a simulation course primarily, though. I know some people I've talked to in the last couple of weeks, they wanted to learn Markov chain Monte Carlo methods, and we are going to do that. And you'll know what those words mean if you don't already. But it is a relatively small part of the course. So I did steer some people away. I said, I think you're going to be disappointed because simulation is not the main focus of this course, but we're going to do it. We're going to do a lot of theory as well. And you can do simulation in any language you want. Most people choose Python, but anything you want is going to be fine. So I am going to put up some tutorials in the R programming language. And I don't think it is great for simulation because it's kind of slow for looping, but it will work for what we're doing in this class because they're going to be relatively small toy problems. And you don't ever need to look at my tutorials. Just pick the language you're comfortable with. The reason I'm posting some R tutorials are for people who are comfortable with nothing. I want to get you up and running in the R programming language and put some tutorials out, and most of you will just ignore them and should. Okay, quizzes. So these are weekly and they're just 3 to 5 questions, and they're very short and they're very basic calculations and definitions. Nothing that you're going to spend a long time on. And these are auto-graded on Canvas. And the point of this was to try to keep you a little more engaged and checking in. It's easy to drift away in a remote course. And I'm not sure that this is going to succeed in that goal. I think maybe I've just spread out what would normally be Tuesday evening panic when you're trying to get your homework done and adding to it. But I'm going to have them available for 2 weeks, which kind of ruins the whole point of being timely and keeping you checking in. But you can retake the quizzes as many times as you want in there. And even if you're past the 2 weeks and you still want to go back and retake a quiz, let me know and I'll open it again. I'm not going to be all hardcore on quizzes like I am on homework. Okay, exams are going to be in the evenings, 2 Thursdays. So Thursday, February 23rd and Thursday, April 6th. They're both from 6:30 to 8:30 p.m. And they're going to be designed to be like an in-class exam, so not that long, but I wanted to give you a lot of time to work on it. The final, I have to look at CU's schedule for when our final is going to be. The exams will be over Zoom, which is not ideal. And we're going to use our usual lecture link. If you can't make those dates because they were not in this, the schedule for this course, let me know. And hopefully you can let me know sooner rather than later, and we will work it out. Okay, the grading scheme. So the quizzes are worth 5%, and the 4 lowest ones are dropped. And there's one every week, except maybe not during an exam week, or, we didn't have one the first week. So there's probably going to be no more than 10 or 11 quizzes, and you get to drop 4. So you get to get rid of quite a few, and they're worth such a small percentage. They're really just a little, again, check-in sort of thing. The homework is worth 25% with 2 lowest scores dropped. We're going to have 2 midterms at 25% each and a final exam at 20%, which is not cumulative. It's just another exam. Some of you are in this course for graduate credit. This course is cross-listed like 6 different ways. There's many things you could have signed up for and ended up in this class. If you are a graduate student, you're going to get an extra problem on each homework assignment. And also, after the Zoom exams, you'll have a take-home portion as well with like 3 extra questions that are a little deeper. And you could potentially be held to higher standards of grading. Although I usually don't do that. I try to hold everyone to the same standards. But yeah, just in case you are looking at some kind of rubric and scoring and someone else has something very different, it may be because one of you is a graduate student and one is an undergraduate student. But again, there probably won't be any difference. I think that's all I need to talk about for the logistics of the course. So I think, yeah, it's time to go. Let's do Markov chains. I mean, that's what you signed up for, so I guess we should probably talk about that. Markov chains or Markov processes, the 2 different words, they have a slightly different meaning that is not important to distinguish between the 2, but we'll talk about the difference between a process and a chain after we get some terminology down. So a Markov process is a kind of stochastic process. So let's start there. The word stochastic essentially means random, and a process is something that evolves over time. When you put them together into a stochastic process, you have something random evolving over time. And by random, I mean mathematical randomness, probability randomness. I don't mean what I like to call street random. If you talk to someone out on the street at a bus stop or something like that about what they think random is, they tend to think it is, there is absolutely no structure. No one can have any idea what's going on. But in probability, we've got some kind of probability mass function or probability density function, and we know how to compute like what we expect to see. And so random in math is not exactly street random. But you put these together and it's something random evolving over time. And more specifically, it is a time indexed collection of random variables. So the time part could be discrete or continuous. And the random variables could be discrete or continuous. So we have 4 regimes here. We could have discrete time and random variables taking on discrete values. We can have discrete time and continuous random variables. We can have continuous time and discrete random variables. And of course, we can have continuous time and continuous random variables. And in this class, we're going to talk about the first 3. So we're not going to be able to talk about continuous and continuous because that involves stochastic differential equations, which is a completely different course. And it's offered by APPM sporadically. It's kind of a special topics thing. So you should demand they offer it next fall. We are going to start off in the discrete time, discrete random variable case. And we're going to spend a lot of time here, like maybe half the semester. So what we have is a sequence of random variables indexed by discrete time, and that's usually integers. Not for the random variables. A discrete random variable doesn't mean it's integer valued, but discrete time usually means time 1, time 2, time 3, and maybe even like an initial time, an initial value for our stochastic process, our collection of random variables. So an x0, x1, x2, etc. And we're using the convention that's always used in probability and statistics that these are random, so capital letters. The process is the entire collection, and we'll usually denote that by putting an xn in brackets. And sometimes outside, we'll have like an n equals 0 to infinity to show us the range of the indices. But because we're going to write this so much, we're often going to leave off the n equals 0 to infinity. But if you have the brackets, this represents the entire collection or process. So again, if you see brackets, it is the entire process. But if you see just an x sub n, this is a random variable. It's not the entire process. It is the value of the process at time n. A Markov process is a stochastic process, and it has a particular property that makes it a Markov process. So a Markov process is a stochastic process that has something known as the Markov property. And the Markov property is something that we define using conditional probability. So before we actually talk about the Markov property, I want to do a little bit of review of conditional probability. And the first few slides, the first few boards that we're going to talk about are probably going to be pretty boring, but let's just get through it so we're all on the same page when we start. Conditional probability. The simplest example I can come up with, maybe I could use a coin, but I'm going to roll a fair 6-sided die. So fair means all of the sides are equally likely. And I want to ask you, what is the probability that we get a 4? And of course, you know this. There are 6 possible outcomes, and they're all equally likely. So the probability we get a 4, which I'm going to write like this, P of get a 4, is 1/6. But now I want to give you some information. So suppose I roll the fair 6-sided die under my desk here, and I look down and I tell you that the outcome is an even number. But for some reason, I won't tell you what it is. I'm just being a jerk about it. So given the information that it's an even number, what is the probability it is a 4? So let me write this out. The probability we get a 4 given it is an even number When you compute that, you are shrinking the universe of possibilities. You are saying, okay, it's got to be even, it's got to be 2, 4, or 6. So now what is the probability I get a 4? And because the 2, 4, and 6 are going to be equally likely, you have a 1 out of 3 chance. So the probability is going to be 1/3. And in conditional probability, we always write given as a vertical line. So it'll be probability we get a 4 given it's an even outcome is 1/3. When you first start studying probability, you usually do it in an event-driven setting. So I'm going to have events, and we denote events by capital Roman letters, usually, like A, B, and C. And so A might be the event that you get a 4, and B might be the event that you get an even number. And I'm a big fan of looking at probability as area in a Venn diagram. So here is a rectangle with a couple of circles in it. And these circles are going to represent the events A and B. And unless you're given some sort of specific information, like A is contained inside of B, or A and B are disjoint, you should just draw them as a couple of circles with some overlap. And if we want to look at the union, I'm sure you're not surprised to learn that that is everything that is an A or B or both and is represented by this shaded area. So that's A union B. If you think of probability as area, you'll be able to remember a lot of rules and also come up with your own. The probability that the event A union B happens, so that means A or B or both, is represented by this area. And that could be broken up into the area that's just in A, so that's the probability of A, plus the area that's just in B. But if you do that, then you will have double counted this inside, this intersection. So we need to take that out. So you may know this rule. The point is that you can come up with any rules, well, not any, but a lot of different rules of probability by breaking this up into pieces of area. For example, the probability that A union B happens, you could take that to be the probability that B happens, and that will be all of the area in B. And then you could take the rest of A. Sorry about the horrible drawing, but you can add to that the probability of A intersected with B complement. Why would you do that? I don't know. It depends on the problem you're given, the information you're given when you have to solve a problem, be it in a textbook or in a real life situation. Sometimes you have some information and not other information. And so Venn diagrams can help you come up with all sorts of rules of probability. And when we think of probability as area, the total area of this rectangle should be 1. And then we're looking at sort of subregions that have probabilities that are between 0 and 1. Okay, so we are ready to define the conditional probability that A happens given that B happened. So in terms of, sorry about that, in terms of a Venn diagram, if you have some A and B, what this conditional probability is saying is that you already know that the outcome is somewhere in the set B, and the rest of the Venn diagram can just go away and disappear. You have shrunk into a smaller universe, and within that universe, you want to know the probability that you're in A, or the area in A. And so for this reason, we can define this as the probability, so the relative area, the probability of A intersect B over the probability of B. And in the die example, let's just do it real quick. So maybe A is the event we get a 4, and B is the event we get an even number. And so the probability we see a 4, given that we know it's even, is by our definition now, the probability we get a 4 and an even number. And that's a little redundant because a 4 is already even, but let's just write out the definition over the probability of an even number. Again, by that redundancy on top, this is just the probability we get a 4 because that already implies it's even over the probability it is even. And we get a 4 1 in 6 times, and we get an even number half the time. And when you divide here, you get the 1/3 again. So all is right with the world. In this class, we are most often going to be doing what I like to call unraveling the definition of conditional probability. As we have just determined, the probability that A happens given that B happens can be written as the probability of A intersect B over the probability of B. And so we could solve for the probability of A intersect B and write it as the conditional probability of A given B times the probability for just B alone. This is what I mean by unraveling this definition. We might not really care about the conditional probability, but instead want to compute the probability of an intersection. And sometimes conditional probabilities are easier. So we want to represent the probability of the intersection in terms of a conditional probability. In your first basic probability course, you probably had some urns and colored balls, and you reach into this urn with this probability and another urn with another probability, and then you randomly select a ball, and someone asks you what the probability that you get a red ball or something, and you think, well, that would be easy to answer if I knew which urn I was in. So if I was given some information. And so sometimes it's just more convenient to write things in terms of conditional probability. So this is one way to compute this intersection. And also, because the probability of B given A is the probability of the intersection, so what I'm doing is a little bit silly, over the probability of the second one, on top, right? A intersect B and B intersect A is the same thing. So let me write it. Let me turn this around. So you can solve for the intersection probability here, and you'll get the probability of B given A times the probability of A. So this is yet another expression for that intersection probability. We have unraveled the definition of conditional probability. There are a lot more things that I would normally say in a probability course at this point. Some of you, I think, are used to seeing next the law of total probability and Bayes' rule and stuff like that. But that's as much time as I want to give that event-driven conditional probability stuff for the moment. Let's move to random variables. And because the first type of random variables we're going to talk about are discrete, let's talk about discrete random variables. So random variables are typically denoted by letters like X, Y, and Z, and the convention in probability and statistic is if it's random, it had better be a capital letter. So if they're discrete, they take on values in discrete sets, and that doesn't necessarily mean integers. The random variable X could take on like 3, 3.1, 3.2, up to 4.0. It's still discrete. And we can talk about the probability that X equals, say, 3.1, or the probability that X equals -1, or whatever. But most generally, we want to talk about the probability that X equals some placeholder, some little x, which I'm making much smaller and a little bit curly to distinguish from my capital X. In this course, we're going to deal with conditional probabilities, and they come from, we first need to talk about joint probabilities. So this is a probability like the probability that X equals some X and Y equals some Y. And in probability is when you're talking about random variables as opposed to events. So if these were events, A and B, it would be an intersection. But we're going to write this as the probability that X equals X with a comma. So the comma means and, Y equals Y. And everything we already know about events and probability can be used here. We can let A be the event that X equals X. And we can talk about intersections and unions and things for random variables. The probability that x equals x and y equals y, and maybe even there's more variables in here, is a joint probability. It talks about more than one random variable, a couple of them together. In the simplest example, a joint probability might be represented by a table, and maybe the x variable can take on the values 1, 2, and 3, and the y variable -1 and 1. And then inside this table, I'm going to put some probabilities. So I'm just making up numbers that add up to 1, hopefully. 0.1. And so the probability that maybe x is 2 and y is 1 is just right down here. It's 0.3. And if you want the probability, a probability for, say, x alone, so the probability that x equals 2, that's going to involve this column. And we have two ways for x. Sorry about that. We have two ways for x to be 2. It could be 2 when y is -1, and it could be 2 when y is +1. And those are disjoint events. Your outcomes for x and y could be 2 and -1, or it could be 2 and +1, or it could be something else. But it can't be both of those together. So in terms of Venn diagrams, we have disjoint areas. And so we can get the probability of both of them happening by adding the individual probabilities. So going back over here to the right-hand side, this is the probability that x equals 2 and y equals -1, plus the probability that x equals 2 and y equals 1. And we can read these right off the table. This is 0.1 plus 0.3, and we get 0.4. And if you want all of those sort of probabilities for x and y alone, you can just sum up all of the rows and columns here. So 0.3, 0.4, 0.3, and then sorry about that, the row totals are 0.5 and 0.5. And so the probabilities for x or y alone are found in the margins. And that's why historically these are called marginal probabilities. Even if the joint probabilities can't be tabulated. Whenever you go from 2 random variables down to 1, you're computing a marginal probability. And also, if you're going from like n random variables down to a subset of all n random variables, that is also known as a marginal probability. Okay, so the probability that x equals x, if we sum over all possible x, we should get all of the probability, and this should add up to 1. And x is discrete, so I can write the sum like this. And I purposely do not write x goes from -infinity to infinity. If x only takes on, the random variable x only takes on a finite number of values, it's okay to write -infinity to infinity. You'll just have a lot of terms that will have 0 for the probability. That's not the reason I don't write this. I don't write this because it makes it look like the only x's that are hit are integer values. So let's not do that. We just saw that if you take a joint probability for x equals x and y equals y, and you sum out one of them, we already summed out y, let's sum out x. You'll get the marginal probability that y equals y. And we are here, we are ready to define conditional probabilities for random variables. The probability that x equals x, given that someone's already observed and told you that y equals y, this is just an A given B. And the definition for this conditional probability is the joint probability that x equals x and, comma, y equals y over the marginal probability that y equals y. For us, and a Markov process or Markov chain, we're going to have a lot of variables, not just x and y, but like an x0, x1, x2 up through xn. And we're going to talk about lots of different conditional probabilities. So let me recap that formula. I just want to emphasize right now that this is just a probability in what I call conditional land. It's a probability in like a shrunken universe of possibilities. And once you shrink, think Venn diagrams from the whole space down to some subset, all the rules of probability still work the same in there. For example, the sum over x of the probability that x equals x given y equals y, it's just a sum of probabilities for x. And if you sum over all x, you'll get 1. And in fact, I wouldn't actually write this. Kind of can mean something else, and it's kind of way non-standard. But just for a moment, we can think about this conditional probability as a probability that x equals x, and then put like a little y subscript. It's just probability in a different universe. So all of the same rules of probability that you know and love apply in conditional land. We talked about unraveling conditional probabilities in the event space with A, B, and C, and let's talk about it for random variables. Because the probability that x equals x given y equals y is the probability of the intersection over the probability that y equals y, we can do the unravel of this definition in order to get the probability that x equals x and y equals y. We can write this in a couple of ways. We can write it in a lot of ways, but using this equation at the top here, we can write this as the probability that x equals x given y equals y times the marginal probability that y equals y. And we can also do it the other way. Probability that x equals x and y equals y can also be gotten by taking the conditional probability that y equals y given x equals x times the probability that x equals x. So we are going to want to find some probabilities like this. And in some problems, it may be more convenient to figure out these other probabilities first and then put them together. So I'm sorry if that quick review was boring to you. If you skipped ahead, this is the point where I'd recommend starting to pay attention. So I'll put that in a timestamp for the video. Suppose we want to find the probability that x equals some x, and it is somehow more convenient to find this if we know the value of y. We could rewrite this as the joint probability that x equals x and y equals y as long as we sum out all the y values. But we can write that joint probability by unraveling the definition of conditional probability. We can write this joint probability as the probability that x equals x given y equals y times the probability that y equals y. You're going to do that so many times that you won't even think about these intermediate step anymore. You're going from here to here. And this expression is, we're computing the probability for x by conditioning on y. Sometimes in a homework assignment or maybe an exam, I'll give you a problem and I'll say, hint, condition on this random variable z. And that's really what you need to do. So drag in a random variable and rewrite it in terms of a sum of conditional things times marginal things. So even that may be a review for some of you, but now we're going to kick it up a notch and we're going to do what I'm going to call double conditioning. Because Markov chains are defined in terms of conditional probabilities, we're mostly going to be working with them, and sometimes it's going to be convenient to bring in yet another random variable. So the idea here is we want to compute a conditional probability like the probability that x equals x given y equals y, and we're going to do it by conditioning on a third random variable that I am going to call z. So I just want to point out first as a note, there is no probability that x equals x given y equals y given z equals z. It just doesn't make sense to write that. Once you're given the information, you put it in a big pile. for most applications, no one cares that you were given one piece of information first and then another. So you really should never write that. You just have everything after the conditional line. And also, where we're going to do this is just like computing the probability that x equals x by conditioning on z, but the y equals y part is just going to come along for the ride. So what do I mean by that? If we want to compute the probability that x equals x by conditioning on z, we should sum over all the possible values of z, the probability that x equals x, given z equals z, times the probability that z equals z. But if we want to do this in conditional land, everything should be given y. So i.e., the probability that x equals x given y equals y, if we want to find that by conditioning on z, we're just going to write what we have above, but every one of those three probabilities will be conditioned on y equaling y. So this is the sum over little z of the probability that x equals x given y equals y and z equals z times the probability that z equals z given y equals y. So what I did was just rewrite this, but every one of those probabilities had a given y. So that's an easy way to remember it, but let's prove that this is true. How would you do this? I'm going to start with the left side. I'm going to drag in a z, and I'm going to write out a definition, and let's just see where it goes. So the probability that x equals x given y equals y, I can sum over all little z the probability that x equals x and z equals z. So I can marginalize out the z, and I can do that in conditional land where y equals y. And then this is a conditional probability. So this is like an event A, and this is like an event B. So I'm going to rewrite it using the definition of conditional probability as the probability of A intersect B, and that's all three of these things together, over the probability of B. So over the probability that y equals y. And there are many ways for me to break this up and rewrite it. I'm going to write it in the way that will get us to what I'm trying to show you. And that is, I'm going to sum over z the probability that x equals x given y equals y and z equals z times the probability that z equals z. Let me get the denominator in there and then go back and tell you how I did that. So this again is like, now this is sum A, and this is sum B. And this is using that unraveling trick, because up here I have A intersect B, and I wrote it as the probability of A given B times the probability of B. So that's just wrong. Let me fix that there. This should be the probability that y equals y and z equals z. Sorry about that. So yeah, now I have it. The probability of A intersect B is the probability of A given B times the probability of B. I can further break down this other intersection over here into the probability that z equals z given y equals y. I could break it down the other way, but I'm going to do it this way, times the probability that y equals y. And once we have that, then we have some cancellation because this is all in the numerator. So this and this are going to cancel. And we end up with the sum over z of the probability that x equals x given y equals y and z equals z times this remaining probability times the probability that z equals z given y equals y. And that's what we were out to show. That's what I claimed on the previous slide. easy in one sense that I'm just writing out definitions, but some of these problems are going to be tricky because, what is A and what is B? And, A consists of 3 things and B consists of 2 things, and I'm taking things out of order. So that's the game to play in most Markov chain problems. Chain versus process. They really mean the same thing. So the word process is a general term, and the word chain is usually reserved for discrete time. So you think of a chain of values. You've got the chain at time 0 and at time 1 and time 2, and you're like linking together a chain. So usually chain is discrete time and process is general, but no one cares if you misuse those terms. Are you ready to define a Markov chain? One more thing I have to get in. So that is that a stochastic process xn has to live on some space, and that's known as a state space. So a state space, I am going to call this S. And this is the set of possible values each random variable can take on. And they need to all be on the same space. And if they're not, if for some reason the value of the chain at time 0 can take on values 1, 2, and 3, and the value of the chain at time 1 can take on values 11, 12, and 13, then the state space just needs to include all of those. And you would say that the value at time 0 takes on the value 13 with probability 0. So this is one space that all the random variables live on, and each xn, each individual random variable, each xn takes values in S. I think we're ready to go now with our definition. This is going to be long, so let me clear the board here. Here is a definition of a Markov chain on a discrete state space and in discrete time. I'm going to let S be a discrete set. In general, I'm just going to call it a state space because that's what it's going to serve as. And then the discrete time stochastic process xn, it's living on S, and it is a Markov chain or Markov process if this is going to be a big, long conditional probability. The probability that the value of the process at time n plus 1 equals some value j pulled out of S, conditioned on or given that the value of the chain at time n is some state I, the value of the chain at time n minus 1 is some I n minus 1, down through the value of the chain at time 0 is some I0. If this is equal to the conditional probability that xn plus 1 equals j given the last value of the chain, then it's said to be a Markov chain. And I have more to write, so there's still some blank space here. But before doing that, let's just talk about this. This right here is known as the Markov property. And I have not finished the definition, but I just wanted to do a really quick example. So the probability that like x3 is 7 given x2 is 1 and x1 is -4 and x0 is 2, this is again an example, is just the probability that x3 is 7 given x2 is 1 if you're talking about a Markov chain. And when we do computations like this, over the equals sign, I'll usually have an MP indicating I just used the Markov property. So to finish off this definition, I just have to put in some fine print. This needs to hold for all times n equals 0, 1, 2 on up, and for all states I0, I1, up through in minus 1, and then I and j in the state space. So is an element of the state space. And one more technicality is wherever these conditional probabilities are defined. This protects you against someone putting something silly back here in the history. Imagine you have a process that takes on integer values and is non-decreasing, like you are accumulating something. You are standing outside of a bank looking very creepy, counting people. And you start with 0 people, and then 1 person comes in. And then the next event, so we'll call that like time 1, time 2, a group of 4 comes in. So now you have a total of 5. And if this doesn't make sense, like this is x0 equals 0, x1 equals 1, x2 equals 5, but then like x3 equals 4, that doesn't happen. And so you could not have been given that. You could not have seen that. And similarly, the conditional probability, you would have a probability 0 in a denominator. So this whole thing would be undefined. But if these two numbers make sense in that they are non-decreasing, then this side may not be undefined. And so we did not destroy the Markov property because we only need this property to hold if both sides are defined. So there's just one more thing I want to talk about for today, and that is, and this is going to be really brief, that missing time steps are okay. And that only the most recent piece of information matters. So for example, if we want to compute the probability that x4 is -1 given x2 is 5, more dramatic, and x0 is 3, we're missing things. We're missing time 1 and time 3, but the Markov property says that this is going to equal the conditional probability that x4 is -1 given x2 is 5. We're going to get this from the definition, and we'll show this next time formally. So to conclude, I just want to say that if you have like a state space, it's not always going to be one-dimensional, but like a y-axis state space and a time axis, and you have some value, and then you have a value and a value, and you've got some kind of random input, then if you're at time 5, where you go next depends on where you are at time 5. So where you go at time 6 depends on where you are at time 5 and some kind of random input, and doesn't depend on where you were before. And that's not to say that the x's are independent, because x6 depends on x5 and x5 depends on x4 and so on. So x6 does depend on x4 and x3 and x2. But once you're given a value, you no longer need the further back history. So we're going to talk more about that next time and prove the claim I made on the last slide about the missing time steps. And we're going to do it all next time on Markov processes. Thank you.
Petunia, show us those hydraulics.